Dear students, welcome to the YouTube channel Mathematics Student Helper. Now I discuss improper integration. This is actually continuation of part 1 of the video improper integration. This is part 2. Here I mainly discussed the convergence of improper integral when the point of infinite discontinuity is an interior point, and then I prove a theorem. Also I give some examples also. I hope that you understand my video. If you can understand after watching my video, please like it and share it with your friends. If the channel is not till subscribed, please subscribe it. Now I will go main topics. Here the domain is a closed and bounded interval, and also function is unbounded, that is the integrand is unbounded, that is the function have infinite discontinuity in some point. In previous video I told that we consider a function a real valued function where a is the closed and bounded interval, that is domain of the function is closed and bounded interval. And suppose f has infinite discontinuity in the domain, then the integration is under improper integral. Okay, now I divide all the point of infinite discontinuity in 4 cases. In case 1 we consider that a is the only point of infinite discontinuity where a is the left boundary of the domain, and case 2 we consider b as only point of infinite discontinuity where b is the right boundary of the domain, and in case 3 we consider that a b are only 2 points of infinite discontinuity of the function. In previous video I discuss all 3 cases and I give examples. Now I will discuss example 4. Here we consider that the function has infinite discontinuity at a point c for some interior point c, that is here c belongs to open interval ab. Here I discuss the case 4, that is the convergence of integration a to b fx dx where c belongs to open interval is the only point of infinite discontinuity. Okay, here the function has only one point of infinite discontinuity. Suppose this is a real line and this point is a, and some right hand side this point is b. Okay, we consider c is the interior point, therefore in the green ball which denotes c, therefore c is a point in the open interval ab. Let f ab to be a function has infinite discontinuity only at the interior point, that is at x equal to c for some c belongs to e. Therefore the function has infinite discontinuity at the point c. You see that such as case 1, case 2, case 3 we have to discard the point c from the domain. So we choose two positive quantities, suppose epsilon in the left hand side and left hand side of c, and then suppose epsilon dash from the right hand side of epsilon. Therefore we consider the open interval and discard it from the domain. However, we divide here the domain, that is ab, in 2 parts. One is a to c and another is closed interval c to b. Now in part 1, that is in a to c, c is the only point of infinite discontinuity and it is the right boundary of the point, which is discussed in under case 1, sorry, is under case 2. Again, if we consider the closed interval c to b, then there c is the only point of infinite discontinuity. It is a left boundary of the domain. Here we consider the domain as c to b. Therefore to check the convergence of the improper integral on a to b, we have to check 2 improper integrals. One is a to c fx dx and another is c to b fx dx. If both the integration converge, then we can conclude that integration a to b fx dx is convergent. Then we have to check the convergence of improper integrals a to c fx dx and c to b fx dx. Okay, we consider the length epsilon from left hand side of c, this is epsilon, and similarly from right hand side of c we consider a length epsilon dash. Clearly this is the epsilon, this must be positive as well as this length must be less than of that length, that is less than c minus a, because if you take epsilon greater than c minus a, then this line will be outside of the domain. Okay, so we take epsilon dash be arbitrary such that epsilon lies between 0 and c minus a, that is length of the epsilon must be less than length of the interval, as well as we have to take epsilon dash such that its length will be less than length of that interval that is less than b minus c, as well, also epsilon is also positive, epsilon dash must be less than 0 to b minus c. Okay, this pink ball is c minus epsilon because this is epsilon. So instead of checking the convergency of a to c fx dx or integrating in that interval, we have to integrate the function a to c minus epsilon, a to c minus epsilon. If the function is integrable on a to c minus epsilon, then if you take epsilon tends to 0, therefore c minus epsilon will converge to c, and the corresponding value of the integration is will be equal to a to c. And in the right hand side we consider a point, this is the c plus epsilon dash. You see that the function is integrable on a to c minus epsilon because the function has only one point of infinite discontinuity, the c. If we consider the domain a to c, therefore c is the only one point of infinite discontinuity, therefore function is bounded on a to c minus epsilon. Okay, since it is bounded, it may be continuous or not continuous. If it is continuous, then it is integrable. If it is not continuous, that is, it may have finite number of point of discontinuity, jump discontinuity. If the function has jump discontinuity at some point, then this will be integrable. Otherwise, if it is it have infinite number of point of infinite discontinuity, then it may not be integrable. However, here we consider it is integrable on a to c minus epsilon. Then f is integrable on a to c minus epsilon as well as c plus epsilon dash to b. Okay. Now we consider phi of epsilon equal to a to c minus epsilon. That is, we integrate f from a to c minus epsilon as well as we integrate f from c plus epsilon dash to b fx dx. Okay. You see that if integration from a to c minus epsilon exists, obviously it will be exist. We consider that exist f is integrable on a to c minus a. This integrable means this is Riemann integrable. Okay. If epsilon tends to 0, then c minus epsilon will tend to c. If you take epsilon tends to 0, then the point c minus epsilon gradually tend to c. In that case, the integration c minus a to c minus epsilon will converge to a to c, provided the limit of phi exists as epsilon tends to 0. Similarly, if you take epsilon dash tends to 0, if epsilon dash tends to 0, okay, this is if epsilon dash tends to 0, then this c plus epsilon will tend to c, because length between c and epsilon, that point green and this pink ball, the length between that two points is epsilon dash. If you take epsilon dash tends to 0, then this comes nearer to c. Okay. So if both the limit exists, then we conclude that both the integration is convergent. Okay. If limit epsilon tends to 0 phi and limit of psi both exist finitely, we say that improper integrals a to c fx dx and c to b fx dx are convergent, and therefore integration a to b fx dx is convergent. Okay. Suppose limit this convergent mean the limit of that exists means it is convergent, and if this limit exists, then it is will be convergent, and hence this will be convergent. Okay, this is integration a to b fx dx means a to c plus c to b. Okay, now if this is L1 and this is L2, that is if limit of phi is L and limit of psi is L2, then integration, main integration, that is a to b fx dx will be integration a to c plus integration c to b, that is L1 plus L2. Okay. Now I give some example. Find minus 1 to 1 by x fx dx. Clearly we have to choose the function fx 1 by x, but you see that in the domain that is in minus 1 to plus 1, the function has no value at the point x equal to 0. So we have to define the value of the function at x equal to 0 separately. So you can choose any real number for the value of x equal to 0, any arbitrary real number, it does not matter. Here I choose minus 7. Suppose fx equal to 1 by 7, 1 by x and 1 by x for x not equal to 0 and minus 7 for x equal to 0. Clearly the function has infinite discontinuity at x equal to 0. So we integrate the function minus 1 to 0 and then minus 1 to 0 and then 0 to 1. If both the integration, that is from -1 to 0 integration and 0 to 1 integration converge, then the function will be integrable from -1 to +1. Now we check the convergence of the improper integrals -1 to 0 1 by x fx 1 by x dx and 0 to 1 1 by x dx. If both the integration converge together, then we can conclude that -1 to 1 fx dx will convergent. Okay. Now for that purpose, you see that in the first integration, that is in the integration -1 to 0 1 by x dx, 0 is the only one point of infinite discontinuity, so we have to discard 0 from the domain. So we take some points left side of 0, left hand side of 0, therefore we have to subtract some positive quantity from 0. We choose this is epsilon, therefore epsilon must be less than 1. That means you have to choose epsilon in such a way that the length of the epsilon must be less than length of the interval, that is epsilon lies between 0 positive it is, but it is less than 0 minus or -1, upper bound minus lower bound, that is 1. Why we choose epsilon? Because we have to integrate -1 to 0 minus epsilon. Okay, we have to neglect the point 0, as well as in second integration we have to neglect 0, therefore we have to add some positive quantity with 0. Here we add epsilon dash, clearly must be length of the epsilon dash must be length of the interval, that is length of that interval is 0 to 1, that is 1, therefore we choose two real numbers epsilon dash. Okay, now here I integrate that from -1 to minus epsilon, and here I integrate from epsilon dash to 1. Here we take it as phi of epsilon and take another as phi of psi of epsilon dash. Clearly fx, that is 1 by x, is integrable on -1 to 0 minus epsilon, and here epsilon dash to 1 it is integrable, because you see that here is no point of infinite discontinuity, and this is a rational function, that is 1 by x rational function, some polynomial by another function, and here it is also polynomial function, therefore fx is continuous on that interval as well as on that interval, therefore it is integrable, that is integral in the sense of Riemann integration, it is integrable on that both the integrals. Now we integrate f from -1 to minus epsilon and f minus epsilon dash to 1. Okay, because we want to integrate it from -1 to 0 and we want to integrate fx from 0 to 1. Okay, for that purpose we consider phi of epsilon from -1 to minus epsilon 1 by x dx, and psi of epsilon dash from 0 plus epsilon dash to 1. Okay, now value of phi, if you integrate 1 by x, this will be log of mod x. If you put upper limit minus epsilon, lower limit -1, therefore this will be log of minus epsilon, that is log of epsilon, minus log of 1, that is log of epsilon. Why you choose phi of epsilon? Because then we have to take epsilon tends to 0, and we have to check the value of phi in the limiting case. If both phi and psi exist, limit of phi of psi exist corresponding limits, that is epsilon tends to 0 and epsilon dash tends to 0, then we can conclude that f is integrable from -1 to 0 as well as 0 to 1. Now we check phi of epsilon, limit of phi of epsilon as epsilon tends to 0. You see that since log x is a unbounded below function, and epsilon tends to 0, if you take epsilon tends to 0, log of epsilon must tend to minus infinite. So phi epsilon tends to minus infinite as epsilon tends to 0 plus. So we conclude that integration -1 to 0 1 by x dx is divergent, and therefore the function is divergent from -1 to 1. The limit does not exist. Okay, I hope that you understand the problem. Now I will back in case 4. Please remind it. Here you see that here C is the point of infinite discontinuity, it is the all interior point. So I neglect C from the domain, so I choose epsilon and epsilon dash. Here I discard epsilon from right hand side, that's therefore we choose a point left hand side of C, that is C minus epsilon, and here we also choose a point C plus epsilon dash from left hand side of from right hand side of C. So we discard C from the domain, then we take epsilon tends to 0 as well as epsilon dash to 0. Now I want to say that here epsilon and epsilon dash are independent, that is they don't depend on each other. Okay, and then we choose phi of epsilon is that and psi of epsilon dash is that, and then I take limit epsilon tends to 0 phi of epsilon and limit epsilon dash tends to 0 psi of epsilon dash. If both the limit exist finitely, we conclude that this a to c integration fx dx is convergent, as well as c to b fx dx are convergent, and therefore integration a to b fx dx is convergent. And if the limit of this is L1 and this is L2, then this will be L1 plus L2. That is a to b fx dx means limit a to c minus epsilon fx dx and limit epsilon dash tends to 0 c plus b to fx dx. This is the L1 and this is the L2, because you say that this is phi of epsilon and this is psi of epsilon dash. Now I say it in a different approach. You see that actually I want to integrate a to b. For that purpose, I break down the interval in two parts. One is a to c and another is c to b. Now we have to integrate from a to c, but we take some point before c. There is some c minus epsilon just before c, and if you take epsilon tends to 0, then c minus epsilon gradually tends to epsilon. So I take epsilon tends to 0. So if the limit exists, as well as here we discard or neglect c from the domain, so we take right side from the c, because here the domain is c to b. We cannot move left hand side of c for that case. So we move to the right hand side of c and to choose a positive real number epsilon dash, and then after integrating the function from c plus epsilon dash to b, we move c plus epsilon dash to c. If in that case move in the sense epsilon dash tends to 0 plus, very small, then c plus epsilon dash gradually tend to c. If that and that limit exists, then we conclude that this is actually a to c fx dx and this will be c to b fx dx. As a result, a to c plus c to b means a to b. Okay, this was the main topics. Now our target is that here you see that here, and this is the result. Here epsilon dash are not independent. Okay. Now if function is integrable, if the function is integrable, then this will be that is both the limit exist finitely. So here since epsilon dash is independent, you can choose epsilon and epsilon dash something satisfying some conditions. Is epsilon must less than c minus a, and here epsilon dash must be less than b minus c, and both are positive. Here we choose, if we choose epsilon equal to epsilon dash, then this is not matter after integrable. If it is integrable or it is convergent, then if you choose epsilon and epsilon dash, that does not matter. This limit must be equal to same. If f is integral on ab, then you can say that a to b fx dash must be equal to limit epsilon tends to 0 a to b c minus epsilon and c plus epsilon to b. I will choose epsilon and epsilon dash. If you limit at a time, therefore the limit epsilon tends to 0 plus a to c minus x fx dx and c plus epsilon to b. Okay, therefore if integrable, the value of integration will be that, or this will be the value of the integration. This expression is called actually Cauchy principle value of the function f when c is the point of infinite discontinuity on the domain AB. Okay, on AB. Clear? So if a function is integrable, then the Cauchy value is exist, and this is denoted by p of integration AB fx, p for principle. Okay, this is denoted by p of AB fx dx. However, if f is integrable, then we find that we see that the Cauchy principle value exists, but converse is not true. But if converse, if so, you have to take the example. Okay, converse is not true means you have to take some examples where the principal value exists, but the function is not integrable on that domain. That is, if Cauchy principal value of the function on AB exists, then f may not be integrable on the domain. For example, we consider the same function fx equal to 1 by x for x not equal to 0, and something here is choose minus 7 for x not equal to 0. You see that x is integrable, is not integrable on minus 1 to plus 1. But here we will see that the principal value exists. This is the Cauchy principal value. Okay, here 0 was the point of infinite discontinuity, so I integrate it from minus 1 to 0 minus epsilon, and then neglecting 0, and then to take another point 0 plus epsilon to 1 fx dx. Here see that this epsilon and this epsilon are same, but in general this is not same, but in Cauchy principal value these are same. Now you have to calculate that. You see that this will be finite. Now put fx equal to 1 by x, here I write down If you integrate fx, this will be log mod x, log of mod x. Okay. Okay. Now if you put the limits, this will be log of mod of minus epsilon, that is log of epsilon, minus of log of mod minus 1, that is minus of log 1. Okay. Limit epsilon tends to 0, log of epsilon minus log of 1. Here this will be log of mod 1, that is log 1, minus log of mod epsilon, that means log of epsilon. Here you see that log 1 is 0, here log is 1 is 0, 0 minus 0 plus 0, here is minus log of epsilon, here plus log epsilon. Therefore both are cancelled. Therefore this will be 0. Okay. So here therefore Cauchy principal value of the function a on minus 1 to 1 exists. Okay. Now we will go a theorem 1. Let f be a real valued function from a b to r. Here actually we find the condition for convergence for positive integrand. Here we consider function of positive integrand as only point of infinite discontinuity at the left end point a. Okay, and it is integrable on the remaining portion. Remain the portion in the sense if you take some point right side of a, suppose a plus epsilon to, then it is integrable from a plus epsilon to b. Obviously epsilon must be lies between 0 to b minus a. Okay, such a function, and also it is positive for all x belongs to open a closed b, because since function has infinite discontinuity at the point a, we are not interested about the value of fx at the point a, so we discard a from the domain. That is we have not interested about the value of fx, so we select here fx as positive on the remaining portion. This is positive. So if it is non-negative, that is if it will be fx greater equal to 0, there will be no problem, nothing. Okay. Now if such a function, that is fx is a positive strictly positive fx, and it has infinite discontinuity at the left boundary a, and it is integral remaining portion, that is from a plus epsilon to b for all epsilon satisfying that. A necessary and sufficient condition for the convergence of the improper integral a to b fx dx is that for every epsilon satisfying 0 less than epsilon less than b, there exists a positive real number lambda such that a plus epsilon to b fx dx less than epsilon. What is this? Actually we have to integrate from a to b, but here I integrate a plus epsilon to b instead of a to b fx dx. Okay, epsilon is arbitrary. If you take epsilon very small, that is nearer to a, if you find that value, if you take epsilon equal to 0.01, suppose you get a value. If you take epsilon equal to 0.501, then we will get a value. If you take epsilon equal to 0.1 crore 0 and then 1, then you will also get a value. If for all for the epsilon you will get a value. Value means it is less than some finite quantity, then it will be integrable. Okay. Before proving the theorem, I want to give you some basic idea about the theorem. Here suppose this is the real line and this point is a, and in the right hand side this point is b. So we have to integrate f from a to b, but we integrate it from a plus epsilon to b. Here the line is epsilon, length of the epsilon, clearly the length will be positive and it is less than to b minus a, length of the integration of original integration a to b. Okay, let epsilon be a real number such that 0 less than epsilon less than b. Therefore the pink ball is a plus epsilon. Okay, if you integrate, here f is integral from a plus epsilon to b, it is given in the statement, but if f is convergent, that is integration of fx from a to b will be converged exist. So if you take a plus epsilon tends to 0, epsilon tends to 0 very small, you see that if epsilon tends to 0, then a plus epsilon is gradually tend to a. Okay, in every point if the integration, that is integration from a plus epsilon to b, if finite, if every point integration from a plus epsilon to b in every point, here see that in every point, every step, in every step you see that in each step nearer to nearer and nearer, also. Okay, if in every step the integration is finite, that is when a plus is nearly a tends to a, in that case also the function value is finite. That is, we say that the function integration of a from a plus epsilon to b is finite, that is it is less than some positive quantity. Therefore there exists a positive real number lambda such that the value of the integration a plus epsilon to b less than epsilon. This holds for all positive epsilon satisfying some condition. Now we will go in proof. Let phi of epsilon means integration of a plus epsilon to b fx dx, where epsilon satisfying that condition 0 less than b minus a. Clearly domain of the function phi is open interval 0 to b minus a. Let us consider 2 points epsilon 1 and epsilon 2. Okay, here actually I will try to give a concept about the nature of phi x. You see that if you take epsilon larger, suppose here epsilon is 0.1 and suppose here a is 1, b is 10. Okay, a is 1, b is 10. Suppose epsilon equal to 1 and epsilon equal to 2. We consider two values of epsilon, one is 1 and another is 2. Here a is 1, b is 2. Therefore the value of when epsilon equal to 1, then a plus epsilon will be 1 plus 1, that is 2. When epsilon equal to 2, the values of f plus epsilon will be 1 plus 2, that is 3. So in first case, when epsilon equal to 1, this will be integration from 2 to 10, and second case this will be integration from 3 to 10. Which is larger? Larger is from 2 to 10, because the range of the integration is larger than 3 to 10. From 3 to 10 is smaller than 2 to 10. So if you take epsilon larger, then the corresponding value will be smaller. So phi of epsilon must be decreasing function. So we have to show it by mathematically. Here we take epsilon to positive, just this is the real line, and here this is a and this is b, and we take that pink ball, that here distance between pink ball from a is epsilon 1, therefore it will be a plus epsilon, and also we take another pink ball, its distance from a is epsilon 2, therefore this will be epsilon 2. So you see that if you integrate that portion, this will be larger than a that, because f is positive and this is the larger domain from that, therefore this value will be positive. Now we calculate it by mathematically. For that purpose we calculate phi of epsilon 1 minus phi of epsilon 2. Phi of epsilon means a plus epsilon to b, so phi of epsilon 1 means a plus epsilon 1 to b, and phi of epsilon 2 means a plus epsilon 2 to b fx dx. Okay, so a plus epsilon to epsilon means from there to b, you have to integrate function, and this means from here to here. Okay, if you subtract that from that, this result will be, this result is a plus epsilon to b, and this is a plus epsilon 1 to b. If you subtract that from that, then therefore the result will be, this is the result. Okay, this is the result, that is this will be integration a plus epsilon 1 to a plus epsilon to fx dx, and it is greater than or equal to 0 since the integrand is positive from a plus epsilon 1 to a plus epsilon 2, because here in the question is given that fx is positive from open a to plus closed b. Therefore this is the portion, if this is f b, it is f is strictly positive from that open, and here this is closed. In that portion f is strictly positive, therefore this will be greater than or equal to 0 since it is integrable. If instead of strictly positive it is greater than or equal to 0, the result will be same. Okay, so we see that phi of epsilon 1 minus phi of epsilon 2 greater than or equal to 0, that is phi of epsilon 1 is greater than phi of epsilon 2. Here you see that thus epsilon 1 less than epsilon 2 implies that phi of epsilon 1 greater than phi of epsilon 2, that is here input is larger but output is smaller, therefore phi is a monotone decreasing function on the domain open interval 0 to b minus a. Okay, 0 to b minus a. So we get phi is a monotone decreasing function on 0 to b minus a, where phi is the integration of f from a plus epsilon to b. Okay, where epsilon lies between 0 to b minus a, etc., etc. Okay, now I give some idea. This is x-axis, y-axis. Here actually this is not x-axis. This is I write down epsilon, and here is epsilon, and vertical line is phi of epsilon. Okay. Here you see that the domain of the function is 0 to b minus a. Here this is 0, cycle to 0, and here suppose here cycle to b minus a. Okay, this is b minus a. Here you see that phi is a function of monotone decreasing. Therefore, this function will be, suppose, in such a way just decrease from that up to that. Okay, suppose this is that phi. It does not reach at the point b minus 1 because its domain is b minus 1, as well as it cannot reach to the origin also. Okay, now you see that now our target is the necessary and sufficient condition for integration a to b fx dx. Okay, now integration of a to b fx dx convergent means limit epsilon tends to 0 phi of epsilon. Value of limit of existence of limit of epsilon tends to 0 phi of epsilon. Now we have to find the condition for necessary and sufficient condition for existence of limit epsilon tends to 0 phi of epsilon. Okay, you see that suppose integration is convergent, therefore the limit exists. Limit exists means this will be finite real number. If it is finite real number, therefore it will be bounded. It will be bounded and it convergent to the supreme of that function, since it is a monotone decreasing function. Okay, because there is theorem, limit open a b to r be a monotone decreasing function, then limit extends to a plus fx equal to supreme of fx. Okay, if limit exists, then it will be supreme of fx. Therefore, it will converge to the supremum of the function. Therefore, if it is bounded, if this is a limit of phi exists as epsilon tends to 0, we can conclude that the function is bounded. Therefore, the value of phi must be less than some real number. Suppose this is the line phi of epsilon equals something. Therefore, all the values of phi of epsilon must be less than that. Suppose this length is lambda. Therefore, we conclude that phi of epsilon is less than lambda. Okay. So here you see that if function is convergent, then phi epsilon is bounded. Okay, and this will be bounded means bounded above, because its limit will be supreme of fx. Here f means phi. Okay, it is bounded here. Lambda is positive because you see that phi of epsilon is less than, but here phi is always positive. You see that phi actually it is greater than or equal to 0. Actually, this is greater than or equal to 0. Okay, therefore this will be positive. Conversely, suppose phi is bounded above. Okay, now we have to find the limit phi of epsilon as epsilon tends to 0. As epsilon tends to 0, you see that if you take epsilon tends to 0, therefore the curve approaches to that in that approach. Okay, the curve along with that portion. If epsilon tends to 0, if then function gradually increase, but after increment it cannot decrease because the function is decreasing. If you take smaller epsilon, the value of the function will be increased. Again, it is bounded, it cannot cross that line. It cannot cross that line. So when epsilon tends to 0, this tip will arise at most that point. Okay, but it cannot cross the upper limit. Again, it cannot cross that line also. It cannot cross that line also. Again, it cannot decrease that portion. Here I mean that this decreasing in the sense. I want to say that this increase that portion. If epsilon test negative, if epsilon decrease, then it will be increase. Okay. If you take decrease, if epsilon decreases, then it cannot be decreased because the function is a decreasing function. If x is size epsilon is increased, then phi will be increased. Sorry, phi will be decreased. So at most, what happens? Just this gradually tend to maximum at this will be the limit. Okay. So if it's bounded, then phi of epsilon must be convergent. Okay. So limit phi of epsilon exists finitely if and only phi of epsilon is bounded above. Is bounded above. Is bounded above means there exists a positive real number, finite if and only if there is a positive real number lambda such that phi of epsilon less than epsilon. For all epsilon belongs to open interval 0 to b minus a. Now phi epsilon means you know that the integration of a from a plus epsilon to b. Here I replace phi of epsilon by a plus epsilon to b integration of fx dx. Just write down that. So again, this means limit of epsilon tends to 0 plus this exists means integration a to b fx dx is convergent. So we conclude that fx dx a to b convergent if and only if there exists a positive real number lambda such that a plus epsilon to be fx dx less than epsilon for all epsilon satisfying 0 less than b minus a. Okay, I hope that you understand the theorem. Hence, it is proved. There is a note here in the statement. I mentioned that f is strictly positive, but it may not be strictly positive. If it is greater than or equal to 0, then there is no problem. The statement is same for that case also. Okay. Now, there is also another theorem. It is for the point of infinite discontinuity at the right hand point. Suppose if it is a relevant function and it has point of infinite discontinuity only at the point x equal to b, that is at the right boundary x equal to b, and it is integrable on remaining portion, that is from a to left of b minus epsilon, that is b minus something. This something must be epsilon. This must be lies between 0 to b minus a. Okay, and also here you assume that fx is positive from closed A open B, because the B point at the point B the function has infinite discontinuity, so we are not interested about the value of f of B. Now a necessary and sufficient condition for the convergence of the improper integration a to b fx dx is that for every positive epsilon satisfying that there exists a positive real number lambda such that integration a to b minus a fx dx must be less than epsilon. Okay, this is same as previous problem, and actually you see that here we have to integrate fx from a to b, but I here integrate from a to b minus epsilon. So we have to choose epsilon very small tends to 0. If every value of epsilon this is finite, so you can take epsilon very small, this will be finite. Again take small, this will be finite. Suppose epsilon 0.001, then this will be finite. Suppose epsilon 0.00001, this will be finite. Suppose 0.100 times 01, then this will be finite. Suppose 0.1001, this will be finite. Therefore, if you take every epsilon tends to 0, then this will be finite. That is its value less than epsilon. Okay. Actually here I not prove the theorem, you have to prove it. I just suggest you prove yourself. Same as theorem 1, you have to consider also phi of epsilon as previous. You will show that it will be monoton decreasing. It is monoton decreasing because if you take epsilon larger, then the value will be decreased, because if you take epsilon larger, then b minus epsilon will be smaller. If you take larger epsilon, suppose epsilon 1 less than epsilon 2, that is epsilon 2 is greater than epsilon 1. Since epsilon 2 is greater than epsilon 1, therefore b minus epsilon will be less than b minus epsilon 1. b minus epsilon 2 will be less than b minus epsilon 1. So range of integration is small, then a to b minus epsilon. Therefore a to b value of integration a from a to b minus epsilon 2 will be less than value of integration from a to b minus epsilon 1. Therefore here phi is also monoton decreasing. Actually you plot the figure, then you can prove it. If you prove, you will show that. I just give some basic idea. suppose here in the previous problem you will suppose this is x-axis and this is y-axis. Okay, at first here you see that suppose this is real line and this is a, this is a, and there is b, and suppose this point is b minus, this is epsilon 1, this point is b minus sorry, I take epsilon to larger, therefore here this is epsilon b minus epsilon 1, this is b minus epsilon 1, and suppose this is b minus epsilon 2. Okay, this is b minus epsilon 2, this is b minus epsilon 2. Okay, therefore here you see that this is from a to b, this is smaller than that. Therefore here you see that this length actually, this is epsilon 1 and this is epsilon 2. So here epsilon 1 is small, epsilon 2 is bigger, but integration from a to b minus epsilon is greater than. So epsilon 1 is small but function is monotone decreasing, but output is less than, therefore function is monotone decreasing. So in the same as previous problem, you have to take a function from such a way, there's just that portion. Okay, so it cannot cross that portion, so it will be convergent. Please try. Okay, I hope that you understand the theorem. Please see the another videos, please see the next video, and obviously you have to see the part 1, otherwise you cannot understand that video. Anyway, thank you, have a good day.